A concrete highway curve of radius 70 meters is banked at a 15-degree angle. What is the magnitude of the force of static friction on a 1,500 kilogram rubber-tired car traveling at 23 meters per second around this curve without slipping? And answers ranging from 7,000 up to 20,000 newtons. Okay, and it's mentioning a lot about a concrete surface and a rubber surface, so I'll just point out that on the first page of this test there was a list of coefficients of friction, and it has rubber and concrete, so it might be not a bad idea just to write down here that mu sub s is 1.00, mu sub k is 0.80, and mu sub r, the coefficient of rolling friction, is 0.02. So that might come in handy. Now this is a banked curve question. This was done in Chapter 8, Dynamics 2, Motion in a Plane. Here on page 217 there's an example, 8.5 turning the corner 2, and in particular here's a nice diagram. So here we have a car. The top view is it's going around some curved path. There's the radius r, and the rear view you show the car from behind. Here's the banked curve, and so now it's going directly down into the page, and it's turning, and there's that radius r. And you normally draw the free body diagram in this point of view as seen from the back of the car. So here it is. I'm going to call mass of the car m. Its velocity is into the page, v. The banking angle of the curve is theta, and the radius of this whole curve is 70 meters is r there. And let's draw the free body diagram for this car. As this view, we always have mg, the force of gravity on the car, pulling it downwards. In this case we have the normal force pushing upwards on the car in this direction, and we also have static friction on these wheels, and we know static friction will act perpendicular to the normal force, but at this moment I'm not quite sure if the static friction would act up the hill or down the hill. If v was 0, I think static friction would act up the hill to keep it in equilibrium, but it's not in equilibrium, it's accelerating towards the left. So I'm just going to guess and say maybe the force of static friction is down the hill. And if when we solve for f sub s and we get a negative number, we'll know we guessed wrong, and that actually it's going back up the hill. So if this is positive, we'll know we guessed correctly. The next thing we have to do is set up a coordinate system. Now we know that the acceleration of this system is just towards the left. This is the A centripetal. And I would like, when I'm calculating these forces, to have all the acceleration along one of the axes. And in fact what they do in Knight is they just set, they call it the r-axis, but I think I'm just going to call it the x-axis to be along the direction of the acceleration. And then I'm going to call, in Knight he calls it the z-axis, I'm going to call it the y-axis to be vertical. So that's the axes, and now all I have to do is draw my little table of x and y components of all the forces that are on that free body diagram. And so the forces in the free body diagram are the normal force, the static friction force, neither of which we know, and the gravity force. And the gravity force is mg. So some of these are going to have to be, I guess mg we know is just going to be straight down, so I'm going to call that negative mg when we add those up, so that'll be an easy one. The static friction and the normal force are going to have x and y components. So let's just draw this out. If this is the normal force, here is normal force in the y direction is upwards, and here is normal force in the x direction is to the left. They're both positive. There's your theta, and I think you'll find sine theta is nx over n, so n sub x is equal to n times sine theta, and n sub y is equal to n times cosine theta. Similarly, we should be careful to look at the static friction force. Here's F sub s, And here is our little triangle. Here is going to be negative f sub s and the x, no, positive. Right, sorry, I chose x towards the left, so that's positive, and then this is negative. F sub s y is in the down direction. So f sub s x, and here's theta right here. So there's a cosine, is f sub s times cosine theta, and f sub s in the y direction is negative f sub s sine theta. So taking all these and plugging them into this table, just looks like that. And now we're ready to compute the net force, F net, on the car. In the x direction, it's going to be n times sine theta plus f sub s times cosine theta is equal to mass times the a sub x, so that's going to be the centripetal acceleration, is equal to mass times v squared over r. And then that's the x component. In the y component, we have n cosine theta minus f sub s sine theta minus mg is equal to the net force in the y direction, and it's not accelerating up or down, so that equals 0 since a sub y equals 0. So as the car is traveling around this curve, it's not accelerating up or down, it's just accelerating purely towards the left. And a sub c is v squared over r. Okay. So now we have two equations and two unknowns. The unknowns are normal force and f sub s. We need f sub s, that's what it's asking for actually. What is the magnitude of the force of static friction? So we're going to eliminate n and solve for f sub s. So if we take this first equation up here, call that star, so then star implies that if we solve that out, that n is equal to mg plus f sub s sine theta divided by cos theta. Okay, and now we're going to plug that into this equation up here. At mg plus f sub s sine theta all divided by cos theta times sine theta plus f sub s cos theta, sorry, just writing that all down, equals m v squared over r. So at this point I'm going to bring this over here and I'm going to multiply both sides by cosine theta. So then I'll have f sub s times sine squared theta, because I've multiplied by cos theta, plus f sub s times cosine squared theta is equal to mv squared over r times cosine theta, and then minus mg sine theta, where we've multiplied both sides. And so sine squared plus cos squared equals 1, so it's f sub s times sine squared theta plus cosine squared theta is equal to 1, is equal to, here, so that's f sub s is equal to mv squared over r times cosine theta minus mg sine theta. So working that out, it's equal to 1,500 kilograms times 23 squared divided by 70 meters times cosine of 15 degrees minus 9.8, again I've pulled out the factor of m here, sine of 15 degrees. So that looks like 1,500 times, open bracket, 23 squared times, this is going to be cosine of 15, I've got it in degrees mode, divided by 70, then minus 9.8 times sine of 15 degrees, close bracket, and I get 7144. So, oops, looks like that. So 71, about 7100 newtons. And so looking up at our answers, that is answer A. So just to note, we didn't actually use this mu sub s, so just to kind of see if this makes sense or not, I want to note that the normal force, we solved for that, we actually eliminated by solving for it, is equal to mg plus f sub s sine theta divided by cosine theta. So plugging that into my calculator, that's equal to mg is 1500 times 9.8, plus we worked out the force of static friction was 7144.8 newtons times sine 15, divide the whole thing by cos 15, and I got 1733. So the normal force is 1733 newtons. So the maximum static friction is mu sub s times normal force. Mu sub s was 1, so it's 17,133. And we found that the force of static friction we actually need is 7,000. So that's greater than this, so we're okay.